Thank you for joining this meeting. This is a joint physical oceanography modeling team meeting. And on behalf of colleagues of the POST and modeling team, I welcome you all to this December meeting. As mentioned, please type your name, affiliation in the chat box. And today's topic is freshwater and heat exchanges between the Arctic Ocean and subarctic seas. And last month, we have a very interesting discussion with the colleagues from Norway who presented observations in the Fram Strait and Barents Sea opening, Laura Distor and Austin Skaggseth. And today we are going to talk about the exchanges between the Arctic Ocean and subarctic seas, but from the modeling point of view. The first presenter will be Wieslaw Maslowski, and the second presenter was supposed to be Evgeny Aksyonov, but unfortunately he had to cancel his talk, and instead of Evgeny, I will be presenting some results discussing the freshwater fluxes in the Fram Strait. At the end of, each talk will be about 15-20 minutes, and after the talk you will have a chance to ask the questions. Feel free to use the chat box to pose the questions. I will try to monitor the chat box. And hopefully after both talks we'll have a little bit of time maybe for discussion. At the end of the meeting we will have members update and we'll talk about the plan next month. Please keep yourself muted so that we don't hear echoes. And with that, Wieslaw, please, it's all yours.
Okay. Can you see my screen?
Yes.
Okay. Put it to. Can you see the slideshow now?
Yes.
Okay. I'll try to finish in 20 minutes, and I assume that someone will keep my time and give me a warning like 5 minutes before. So this is a work that basically is a collaboration among a number of groups, and I apologize if I missed somebody's name on the co-authorship list, and I'm using their results. But basically, we're trying to look at the model representation of the oceanic heat convergence in terms of the ocean contribution. So the outline of the talk is just I'll provide some points on motivation. I'll provide an overview of our regional Arctic system model, which I'll show a lot of results from. And I'll talk about modeling pan-Arctic oceanic heat convergence. We'll focus on the Barents Sea fluxes and heat convergence over just the Barents Sea. I'll provide some intercomparison of model Barents Sea opening volume and heat fluxes, and I'll provide some summary. So one of the motivations is that if you look at the upper row from observations, there's a paper published by Agnieszka Baszczyńska-Miller with some additional papers by Skaggseth et al. 2011 and Kerr et al. 2013 for the Norwegian coastal current and the Davis Strait. And you put those numbers together from Strait about 2 Sverdrup south, Barents Sea opening, Davis Strait, Bering Strait, runoff, precipitation minus evaporation, sea ice outflow. You add them together, those mean numbers, and the volume is not balanced to zero. Whether you take the higher value for Davis Strait or lower value, you get order of -1 point Sverdrup or 0.8 Sverdrup imbalance from those mean published values. When you look at the individual year estimate by the inverse model published by Tsubuchi et al. 2018, there's a small imbalance, but the numbers dramatically change. For example, in particular in the Fram Strait from -2 to -1.1. And also the Davis Strait is somewhere in the middle between the high and low value published before. We published some time ago in 2004 a paper where we look at the 9-kilometer model, and our volume budget had to balance, because in the model we cannot be having sinks or sources. So the number shown here under NPS name model are the estimates of that particular model, suggesting net fluxes in a mean sense in and out through those main gates. And then if you look at the global ocean ice models, the paper summarizing the global ocean force with the Core 2 reanalysis by Ilichak et al. 2016, you can see that an individual model can have a value in the Fram Strait like 1.3, and other numbers are maybe comparable. The multi-model mean of 15 models has a much higher value of Fram Strait, higher value of the Barents Sea opening, lower value in the Davis Strait, and higher value in the Bering Strait. So altogether, one of the things that the CMIP 6 CSM2 11-member ensemble contribution that is currently being worked by Matt Watts, a PhD student at NPS, is providing the lowest estimates in this table. And again, you can see that the numbers vary a lot. The main issue here is that the modeling numbers definitely will vary with different models, but if we don't have constraints from observations, which are close to zero volume budget, it's hard to evaluate individual sections in terms of volume and then heat fluxes and other properties like freshwater if those numbers are not budgeted to zero. So that's the first motivation. Second motivation is that if you look at the upper panel here, and the purple line representing the ice extent anomaly time series relative to the ocean heat content anomaly in the upper Arctic, you can see there's a correlation. Correlation is order of 0.7, and there's no lag. So basically, with this regional Arctic system model, we can see that oceanic heat convergence and the respective oceanic heat content have a strong effect, has a strong effect on the sea ice cover in the Arctic in the long term. Another motivation is that if you look at a winter surface heat fluxes on the left panel, the blue color represents order of 200 or more watts per square meter in a mean sense, a winter mean sense, and that's a multi-year winter mean, 1980-2019, which is suggesting that if we don't get the right transport of warm Atlantic water into the Barents Sea and into the Arctic, it's not only that we might be missing representation of the sea ice, but also the air-sea coupling might be actually not represented well as well. And if you look at this map on the left, surface heat fluxes in the Barents Sea are order of 200 watts per square meter in the winter mean, and the maximum values both in the West Spitsbergen current and the East Greenland current and the Labrador Sea are up to 400 watts per square meter in the winter mean. So just a brief overview of this regional Arctic system model. I will be showing some results which are based on this model, and we can have a different combination or different model configuration where the atmosphere is typically 50 kilometers, but it could be replaced by the atmospheric reanalysis. And then the ocean could be either 9 kilometer or 2 kilometer, 2.4 kilometers, 45 levels or 60 vertical levels. And then we can also note that this model doesn't use any data simulation, and there's no ocean temperature salinity restoring. So it's just driven by reanalysis or the external global forcing. So I'm showing here a summary of different model configurations. Most of them are reanalysis force. So the G letter at the beginning stands for the ice ocean force with reanalysis. The RBR is a fully coupled model. And then we have a different model configuration where 9 is representing the 9-kilometer grid for the ocean sea ice. 2 represents the 2.4 kilometer, and then the 45 or 60 is representing the different vertical levels. If you look at the ranges from those different model configurations for Fram Strait, the same model with different resolution and different way of coupling or forcing with analysis for the Fram Strait can be ranging from -0.5 to -0.28 Sverdrup. For the Barents Sea opening between 1.2 and 3.11. For Davis Strait from -0.2 to -1.82. And then the Bering Strait order of 0.7, 0.8. So a single model can also vary a lot depending on the resolution, what forcing we apply from the atmosphere, whether it's a fully coupled or prescribed atmospheric forcing. So here I'm showing a comparison of the fully coupled model at 9 km 45 levels in the vertical on the left, and the equivalent configuration but forced with atmospheric reanalysis, 9 km 45 levels. If you look at those numbers under each plot, for the forced model, the oceanic heat convergence is order of 10 terawatts. For the fully coupled model equivalent configuration, it's almost twice as that. And then if you look at the use of the reference temperature, whether this is 0 degrees Celsius or the freezing temperature, for the heat convergence, the numbers don't change almost at all, but the directional fluxes vary quite a bit. The resolution might be important in terms of how well will represent the various currents. I'm showing two panels here, where the left panel is showing the eddy kinetic energy within the Fram Strait region from the 9 km 45 vertical levels forced ice ocean simulation. And the right panel is showing very similar configuration, but with 2.4 km resolution in a horizontal. So you can see that with increased resolution, we resolve more eddies. Those eddies might provide some means for recirculating the Atlantic water into the East Greenland current back to the East Greenland current, or they might be allowing some transport of water across Fram Strait into the Central Arctic. So the complex circulation eddy activity at Fram Strait, which Dmitry will talk more about this, might affect not only the volume freshwater fluxes or heat fluxes across Fram Strait, but also will be a very important contributor to the overall oceanic heat convergence into the Central Arctic from all different sources. So now if you look at the oceanic heat convergence between different model configuration, the numbers can be varying from for the fully coupled model about 8 terawatts, and for the 60 level 9 km forced ice ocean model can be twice as that. Okay, and there are different changes with resolution, not necessarily that increased resolution necessarily increases the oceanic heat convergence, because in some cases eddies might be helping to recirculate water instead of converging into the Central Arctic. So now I'm showing some comparison of the different model cases where we look at the oceanic heat convergence into the Central Arctic, including the Barents Sea and Kara Sea. And in this case, I'm showing a G case, which is the ice ocean force model at 9 km 45 levels. And we have a total for Pan-Arctic 83 terawatts and roughly 3 or 4 terawatts only converging into the Central Arctic. 95% of that heat convergence is being lost over the Barents-Kara Sea, as it's shown on the left panel. With this much heat lost over the Barents-Kara Sea and very little heat converging into the Central Arctic, the sea ice at the end of the simulation in December 2009 looks quite realistic, maybe a little even too thick in terms of the ice thickness distribution, where we still have in December 2009, we have order of 2.5, 3.5 meters in the Central Arctic. If we go to a different case, a fully coupled simulation, again, 9 km and 45 levels, we increased from 83 terawatts for the Pan-Arctic to 102 terawatts. So we increased our order of 20 terawatts in the Pan-Arctic sense. But if you look at the Central Arctic oceanic heat convergence, we gain order of 10 or 12 terawatts in the Central Arctic. And we are losing less over the Barents-Kara Sea, as you can see on the bars for the Barents-Kara Sea in the left panel. If you look at the ice thickness distribution and at the end of the simulation, you can quickly see that actually ice is thinner, which somehow suggests that the increased oceanic heat convergence into the Central Arctic has an effect on the ice thickness distribution at the end of the simulation after order of 40-year simulation with a fully coupled model. Now, if we look at the different fully coupled run where we modify some parameters and some forcing, but it's still fully coupled model. From one case of fully coupled model, we had 102 terawatts. If we increase by order of 40 terawatts Pan-Arctic heat convergence, or another 18 terawatts into the Central Arctic, now we're looking at roughly about 30 terawatts Central Arctic heat convergence. In this simulation, the ice disappears in summer. So December 2019 panel on the left is showing newly formed ice, less than half a meter or so, that just formed this winter since all the ice in the Central Arctic has melted that summer before. So with this much ice, oceanic heat convergence into the Central Arctic, RASM, the Regional Arctic System model, suggests that we might be melting ice altogether. I wanted to point out that observationally based estimates based on inverse model estimates for 2004-2010 are suggesting that we have been having in the past oceanic heat convergence for the Pan-Arctic order of that in that number of 136 to 169 terawatts. So whether RASM is doing something wrong or those observationally based estimates are maybe with some uncertainty, that's something to be determined. But the bottom line again is that we need observations for constraining models. So if you look at the oceanic heat convergence between two cases where we have ocean ice forced with JRF 55 reanalysis, the 9-kilometer oceanic heat convergence suggests that we have order of 66 terawatts versus 1 degree ocean ice model with the same ocean code, the RASM ice ocean code, suggests 5 times less, basically. Okay, and recently published paper by Ann Wen et al. 2020 estimates the Barents-Kara Sea convergence in the similar ballpark as our estimate here, at least with that resolution about 9 kilometers. So there is some agreement about between models and the inverse models approaches. If you look at the Barents Sea opening and look at the left panel, you can see that with the high resolution, this is a 9 kilometer or 1/12 of a degree, we have the Norwegian coastal current represented by freshwater by the Norwegian coast in the lower left panel, and that Norwegian coastal actually current for the September 1983 in this simulation is even warmer than the Atlantic water flowing into the Bear Island Trough from the Norwegian Sea. If you look at the comparable September 83 from the 1 kilometer, you don't see the signature of the Norwegian coastal current, and the inflow is significantly lower. So only high resolution RASM simulation, which is shown on the left, can realistically represent the temperature salinity structure at BSO, Barents Sea opening, including the Norwegian coastal current. Norwegian coastal current has a distinct temperature salinity characteristics compared to the inflowing Atlantic water into the Bear Island Trough, which is Norwegian coastal current being warmer, fresher, and it's also flowing faster, which is indicated by the black contours in this on those panels. If we compare the 1 degree and the 9 kilometer forced ice ocean simulation across the Barents Sea, so we basically go from the Norwegian coast on the left to the Svalbard on the right, you can see that 40 kilometers or so within the coast, what we call Norwegian coastal current, it's defined for the volume flux, and then I'm sorry, I mislabeled. The left panels are the 1 degree. The right panel is the 9 kilometer. It's the reverse here. So the 1 degree model doesn't represent the Norwegian coastal current much at all, but it has very weak inflow, and the Norwegian coastal current, whatever we call, is somehow balanced by the outflow between Bear Island and Svalbard. If you look at the heat fluxes, the Norwegian coastal current accounts for order of maybe 38% of the total heat inflow into the Barents Sea. For the temperature reference at freezing temperature, if you use the temperature reference 0, it accounts for about 30% still. On the 9 kilometer, we're showing that the volume contribution from the Norwegian coastal current, it's about 48% of the total. Very little outflow between Bear Island and the Svalbard. And the heat contribution by Norwegian coastal current actually is more than the net contribution by the Atlantic water, which is inflowing into the Bear Island Trough. Very little contribution for the northern subsection of the Barents Sea opening. So on the lower right panel, I'm showing this red arrow, which is a location of the moored arrays that has been maintained by the Norwegian scientists and Norwegian institutions for some time. And the point here is that mooring array is not accounting in the long-term monitoring sense for the Norwegian coastal current, and it's also not accounting for the potential outflow within the Bear Island Trough. So if you look at the eddy kinetic energy from 2 different model configurations, 9 kilometer and 2.4 kilometer, forced with reanalysis, you can see that there's a significant eddy activity at the divergence zone where the Norwegian Atlantic current splits into the West Spitsbergen current and the inflow into the Barents Sea. And the eddy activity is extremely high, order of 2-3 times higher in the 2 kilometer model than in the 9 kilometer model, suggesting that the contribution along the coast might be significantly driven by the eddies. We also have done some sensitivity studies where we, by having a regional model, we basically were able to increase or manipulate the volume fluxes across Barents Sea to see how the volume fluxes are responding, or how the heat fluxes across Barents Sea opening are responding to the increased oceanic volume fluxes. And basically it's a pretty linear relationship. With more volume, you have more heat coming through the Barents Sea opening. Now, the right panel is showing that with the increased oceanic heat inflow across the Barents Sea opening, we also increase the oceanic heat convergence within the Barents Sea. So most of this water heat delivered by Atlantic water is lost over the Barents Sea. The more heat you enter through the Barents Sea opening, the more heat you lose over the Barents Sea. So I think I should wrap up. Basically, if you look at the different models, and I'm listing those different models in this table here. So there's a E3SM ice ocean force simulation with 10 kilometer refinement in the Pan-Arctic, or 6 kilometer in the Pan-Arctic. This is UKMet global Earth system model at 112 degree. HICOM sea ice ocean model either at 112 or 124th degree. The NEMO, ANHA, quarter degree in 112, and 3 different configuration of the RASM, 1 degree, 112, and optimized. And compare this to the estimates from observations, what you can see that most of the models, specifically even those with high resolution, are suggesting the net volume transport across Barents Sea opening order of 2.73 Sverdrups, and the respective heat fluxes order of maybe 80 to 100 terawatts, compared to 2.2 or 2.3 Sverdrups from estimates only for that middle section, not accounting the Norwegian coastal current and not accounting the recirculation part, and the 73 or so terawatts of outflow. So general volume and heat fluxes at Bering Sea opening increase with model resolution. And we believe that this is in part due to the improved representation of the Norwegian coastal current influx into the Barents Sea, which is possibly not fully accounted in the published observational estimates, which I'm showing here at the bottom. So in summary, I would suggest that RASM simulated Arctic sea ice cover is sensitive to changes in oceanic heat convergence, and it's a function of model configuration and resolution. The Barents-Kara Sea removed a large quantity of oceanic heat delivered into the Pan-Arctic, order of 90% or so of the total, which makes this region very critical in terms of its potential impact on the lower latitude weather and climate, as well as if we don't represent the oceanic heat convergence over the Barents-Kara Sea, we will affect how much heat is delivered into the central Arctic. And I've shown some results where there is an implication that this oceanic heat into the central Arctic may significantly affect the ice cover or ice melt in the Arctic. There are large uncertainties that persist in observationally and model estimated Arctic-wide volume and property fluxes. And finally, improved observational estimates of Arctic-wide volume and heat budgets are necessary for constraining model, climate model simulations and projections. I'll stop here. Thank you.
Thank you, Wieslaw. And are there any questions, comments? Okay, well, people are, okay, yeah, Maria-Louise, please go ahead.
Yeah, thank you for a nice talk, Wieslaw. I have a question about eddy kinetic energy. I'm wondering if do you have any sense of a validation for that, or have you validated in any way your EKE?
Right, so I'm not sure if I'm aware of something that could be used for model comparison of eddy kinetic energy in the Barents Sea, but we published a paper some time ago where we look at the Labrador Sea, and the 9-kilometer resolution model was capturing order of 70% of the observationally estimate eddy kinetic energy for the period of the mid-1990s in the Labrador Sea. The locations of eddy kinetic energy in Labrador Sea were quite realistically, skillfully represented. There is a secondary eddy kinetic energy. I'm referring to a paper by Jonathan Lilly et al., forgot the year, but they showed one eddy kinetic energy maximum in the southern Labrador Sea and one in the central eastern Labrador Sea, right next to the Greenland coast. The model estimates at 9-kilometer resolution were capturing order of 75% of that secondary maximum in eddy kinetic energy.
Thank you.
This is Patrick. I could ask a question. Nice talk, Wieslaw. The next to last slide that you had with the different transport estimates through the Barents Sea opening, if you had some sort of uncertainty estimates, and they could be maybe just even based on standard deviation from variability, so let's say monthly means or so monthly values, or however you wanted to frame them, would be interesting to have them, and also to see whether they are a function of resolution, right? So maybe that's larger.
So Patrick, I fully agree with you, and the reason I don't have those standard deviation estimates or whatever quantification is that I didn't have them for all those models. I decided that
Okay.
I will not be showing just only for some. Like, for example, the two models configuration that Dmitry provided, we have the uncertainty or standard deviation. Same for the RASM simulations.
Okay.
But I don't think I had this for all other models. The list which was shown at the very beginning had some uncertainty estimates based on observations and the some of the models as well. Here, those are observational estimated uncertainty, and we can actually show the same thing for the model. So in general, I think that the model uncertainty or standard deviation tends to be on the smaller end compared to the observational estimates.
Right. Yeah, and it's good to see how large some of the observational estimates actually are, right? The uncertainties. Yeah.
Yeah, so the uncertainty in observations is basically, you know, well, I'll probably let other people to talk about that better than
okay.
me.
Yeah. Okay. No, but thanks. Yeah.
One last question before we go to the next presenter. If not, then Wieslaw, I have a quick question.
Dmitry,
Yes.
the question in the chat box.
Yep. What observations would best constrain models? What observation collection should be prioritized? And couldn't be improved observational data set address the issue of models yielding different results as a function of model resolution? So I was thinking how to present this, and by no means I'm trying to criticize the imbalance in the volume or other properties based on observations. I realize that that's a very challenging work. To the contrary, I think that the modeling community and observational community should work together to help each other. Basically, the modeling community may help observational groups to justify more and better funding and long-term funding to continue those measurements and further refine those measurements. And I provided I focused on the Barents Sea opening because it's a clear winner in terms of how important it is, how much heat flux is delivered into the Barents Sea, and how much is being lost over the Barents Sea. So other gates such as Fram Strait and Davis Strait are also very important, including the Bering Strait as well, where warm water gets on the shelf and then it's immediately going into the deep Canada basin. So from that perspective, I think that it's a challenge. It's a big challenge, especially in places like Fram Strait. But we should communicate. We should try to help each other to provide better justification to come up with better observations, more refined observations, and then work with modeling community to help them to constrain those estimates from models.
All right, thank you, Wieslaw, very much. And we have to move on. Okay, next presenter is myself. All right, so today's presentation is closely related to the talk given by Laura Distor last month, where she talked about observations in the Fram Strait, on the West Fram Strait. And today we'll be talking about the same observations, but from the modeling perspective. And the idea of this talk was motivated by multiple discussions during our famous meeting in the past, meeting led by Andrei Prushtinsky and Mike Steele, where we try to understand the uncertainty, not only models, but also observations. And we try to use a combination of both models and observations, trying to suggest the better observational approaches and better modeling. So try to help each other to understand better the Arctic system. Okay. how can I progress here? For some reason, okay, maybe like this. All right. Yeah, so we know that observations are not perfect, and especially in the Arctic, where it is really challenging to collect observations. And there are a lot of sources of uncertainty, which I'm not going to talk about all of them, of course. And there are multiple publications which discuss different type of uncertainties in observations. On the left is one of this example, the paper that I found yesterday, which discussed problems with they found with more observations in the Fram Strait. And today our focus is how much are we missing on the northeast Greenland shelf. As you know, the existing mooring observations, they cover not the whole Fram Strait, they mostly cover the deep part of the Fram Strait. And here you see locations of the existing mooring array, the current mooring array 2016. And the mooring array is supported by two groups from Norwegian Polar Institute and from Alfred Wegener Institute moorings. The Norwegian NPI moorings are on the West Fram Strait, and AWI moorings were in the central Fram Strait and eastern Fram Strait. Note that since 2016, AWI removed some moorings in the central Fram Strait, and this is the current mooring array in the Fram Strait. So we don't have observations in the central part of the Fram Strait, to my knowledge. So my question is, how much are we missing over here? And we had a lot of discussions with Laura Disteur and Wieslaw and Paul Myers. So what can we do trying to understand what are we missing in terms of freshwater flux, heat flux, and can we help observational groups to somehow reduce all this missing information? As I mentioned, there were several adjustments of the locations of the mooring during the period of observations, and there is a lot of discussion and explanation in the paper published by Laura Disteur and co-authors in 2018. But here you're looking at the transport freshwater flux derived from the mooring observations during different time period and during different locations of the moorings. Here I'd like to draw your attention to the fact that adding just one mooring, F17, on the very edge of the northeast Greenland shelf drastically changed the freshwater transport estimate. The blue line you can see compared to the yellow line without this mooring, it resulted, for example, in the year 2010-2011, almost 2 times larger magnitude of the freshwater transport through Fram Strait. So in order to estimate the uncertainty, I use a model, HICA model, which I'm going to introduce briefly in the next slide. And I'm interested in this region, the region which is roughly 240 kilometers from the coast to the first mooring on the shelf. It has a very complex topography, which is shown here. And I assume this, that the rest of the Fram Strait is covered by this set of moorings. Remember that we don't have moorings in the central Fram Strait any longer since 2016. And the yellow line shows the section in the model, which closely follows the allocations of the moorings in the West Fram Strait. The model that I'm using for this analysis is 1/12 degree. This is equatorial resolution. It is quasi-distant, equally distant in the high latitudes, which is roughly 4 kilometers in Fram Strait. The details of the model are given in these 2 papers in 2016 and 2019, and I'm not going to spend a lot of time on explaining the model, but I would like to show the animation which some of you already seen before. It shows the distribution of Greenland freshwater. And look here what is going on the northeast Greenland shelf. There is quite interesting circulation going on here. We can see that freshwater kind of accumulates on the Greenland shelf during summer. You cannot see the months, unfortunately I'm not showing them, but during summer there is some kind of accumulation going on here, and then all this freshwater is flushed southward. And we're going to see why this is happening. The model has been validated, and some validation was presented in the papers that I referenced in the previous slide. For the Fram flux estimates, I can say that the model agrees very well with available observational-based estimates. In volume flux, you see it has very good agreement with previous studies. Freshwater flux, well, heat flux, it depends on the reference temperature because we are talking about the not closed contour, so it's kind of sensitive. Let's look at the upper ocean circulation derived from the model. The panels show the 50-meter average circulation from HICAM shown by months. And as you can see, there are two distinct circulation patterns. In May, June, and July and August, there is weak anticyclonic circulation develops during these months, which is probably well established in July. And the rest of the year, the shelf is dominated by very strong southward flows, especially in November and December. That's what I said. And I think that this is related to the wind-driven dynamics, because in May and September, the winds are relatively weak and they goes from both directions, but the rest of the year, the shelf is dominated by very strong, persistent northerly winds. Note there is different scale. The circles show the probability of observing winds from these particular beams, and the colors show the wind speed. So very strong northerly winds dominate the shelf, which explain the establishment of this southward flow during the winter months. If you look at the vertical section, which shows the mean speed and standard deviation in contours from HICAM, well, we see the dominant features, the East Greenland current, recirculation current, and West Spitsbergen current. On the shelf, the flow is predominantly southward, but here in the north wind trough, it is interesting. It seems there is persistent feature which goes northward. And I also checked with Wieslaw and Paul, and their models also show these persistent features, well, at a different degree of strength. RASM has slightly weaker flow, as far as I can tell, but still it is there. We also know that a lot of fresh water sits on the Greenland shelf. And next, I'm trying to estimate the freshwater content over the northeast Greenland shelf compared to the overall freshwater content across the Fram Strait. And I calculate the freshwater content going from Greenland coast to Spitsbergen. So the horizontal axis is longitudes, and the vertical axis in this panel shows the freshwater content in meters of freshwater. And you can see that most of freshwater content, there is a lot of freshwater content on the Greenland shelf, and most of it, this is the integrated freshwater content, is, or at least 50% of it, is right before the mooring. These are the Hofmüller diagrams showing the volume transport and freshwater transport over the Fram Strait. The dash lines show the mooring locations. The F-17 is the last location on the west Fram Strait. And we can see that in terms of the volume flux, the contribution of the Greenland shelf probably is not that big, but it may be more significant in terms of the freshwater flux. We definitely see seasonality here. You see this dark blue spots that correspond to the strong southward transport of fresh water during winter months. So next, I calculated the volume and freshwater fluxes across different segments of the Fram Strait. Note the color codes. They correspond to the segments S1, this one, which is not covered by observations, S2, central Fram Strait, and S3, this is the Svalbard shelf, which doesn't contribute a lot, so I'm not going to talk about this one. But S1 is interesting. In summer, the contribution is almost zero. This is the volume transport. And the numbers correspond to the fraction of the transports explained by S2 segment, okay? But in winter, the contribution of S1 increases up to about 15–20% in November, December months. The freshwater flux have similar pattern. Also, again, a very small contribution in summer months. And remember, this is the months when the survey cruises taking place in Fram Strait. So during these months, the surveys cannot observe a lot of freshwater flux over this segment. And a lot of freshwater flux occurs in winter months during the segment S1, which goes up to, if I remember correctly, 30%. So these are my summaries for this, which I already talked about. So next, I try to estimate if we can somehow reconstruct the missing information given the observation on the Greenland shelf with just one mooring. And I did a simple linear regression, hoping that this transport can be reconstructed from the observation on this F-17 mooring. And I found that the correlation between the freshwater fluxes on the shelf, on the Greenland shelf, and observation at F-17 mooring are not really high. So there is F-17 mooring observations cannot provide enough information to reconstruct the at least freshwater flux on the Greenland shelf. Okay, I think with this, I'm going to the conclusions. So the model suggests that there are two patterns of ocean circulation on the northeast Greenland shelf. In summer, it's weakly anticyclonic, and then during the rest of the years, the shelf is dominated by strong southward transport of fresh water and volume. We also saw that a lot of fresh water is stored on the Greenland shelf, and given the very strong transport and very low salinities during the winter time, the contribution of this segment S1 is very significant in terms of the overall transport of fresh water through the Fram Strait. Yeah, and I think this is it. And I'm ready to answer the questions. If there are any questions, please.
I have a question.
Yes, please.
Just to make sure I'm understanding correctly. So you actually see the most freshwater flux at the time of year that you would expect the least amount of delivery of fresh water from the Greenland ice sheet itself, but the limiting factor seems to be the transport, which you're pointing out is driven, in fact, by the winds happening in the winter, which is offset from when that fresh water is actually delivered, dumped into the ocean from the ice sheet.
Yes, but the fresh water on the Greenland ice, on the northeast Greenland shelf, is not only from Greenland ice sheet. The reason I showed this animation just to draw your attention to the fact that during summer we see kind of accumulation of this fresh water. Not only this fresh water, but fresh water transported from the Arctic Ocean is also accumulated on the shelf, and then it's quickly removed by the winds to the south. If we talk about the Greenland runoff, there is some delay by the time the fresh water transports from Greenland ice to shelf. I haven't looked at the northeast shelf when the peak of this concentration occurs, but it is delayed probably by 1 month after the highest runoff from Greenland land.
Thank you.
Yeah.
Hi, Dmitry. I have a question if it's time, and Lars here. So,
yeah, Lars.
I understand you correctly if you say that so there's a lot of fresh water sitting there, but it's only in the winter when you have the strong winds that you see a significant transport on the shelf, right? But then did you look into correlations towards the wind forcing, or is that difficult because of the sea ice cover, or, you know, so what do you think drives the variability then?
I think it's wind. I think it is wind. I haven't looked in detail into this, but I think it's so obvious. The shelf is relatively shallow, most of it, and I would assume it's wind-driven dynamics.
Yeah, so just an Ekman transport towards the shelf, and so you could also maybe look at the surface slope if you get that from satellite, right? So that you could estimate that volume transport either by looking into the wind forcing or looking at the surface slope.
Yeah, but it's mostly sea ice covered all year round. This part of
I know. Yeah, but you could still look at the. Oh yeah, you need the sea ice thickness, of course, as well, and that might vary. Yeah, you're right. Thank you.
Yeah.
So this is Mike McCracken. So I'm a little curious. Is that freshwater flux also includes sea ice flux that's going, so that it's or is it actually water below the freshwater content, sort of below sea ice?
This is only oceanic freshwater flux. There is no sea ice in this calculation.
So even though it gets very cold, there's no sea ice formed? No,
there is in the model. I just didn't include the amount of sea ice into the freshwater flux calculation.
Okay.
No, there is sea ice, of course.
Roughly half that. Oh, it's a big contribution from the sea ice export itself. Yeah. I mean, the sea ice is thinning, so the volume transport is probably going down, but it's roughly the same amount of fresh water. It's a lot of sea ice coming out every year.
Yes, sea ice flux is a different story. Although we observe relatively well the sea ice flux through Fram Strait, at least in terms of the area flux, there is some uncertainty with thickness estimates from satellites. But to my knowledge, these estimates are quite reasonable. So we have a good understanding of the sea ice fluxes through Fram Strait. Am I correct, Lars?
Isabella, you're here. I forgot the numbers you worked out, but you looked in. You made that calculation, didn't you?
No, I didn't calculate sea ice flux.
No, Isabella Lebras did.
Oh, okay.
She's in the audience. I forgot the numbers now, but.
Yeah, I can. I'd have to look them up as well right now. I don't have them on the top of my head.
But it's significant. It was a quite large.
It's the reference salinity, right? It's hard to compare sea ice flux and liquid freshwater.
Mm-hmm.
Yeah.
Well, your references.
Yeah. Well, but you could, like you did the pure freshwater flux, right? So just how much fresh water you have. Oh. But yeah, but I think they're comparable.
It's definitely significant.
Somehow my recollection is that the sea ice freshwater flux might be even higher at Fram Strait than the liquid one.
Yes, it is. Sea ice volume export is still larger than the freshwater transport, the oceanic freshwater transport.
Yep.
Although it's been declining very fast the last 2 years.
Yeah, that's true. With the thinning sea ice, the area doesn't cover that, so we don't know much. But there used to be upper-looking sonars that up in the Fram Strait that were providing some estimates of the thickness of the ice. Is this still there, or this is all
yes,
gone?
They're still there, and you can expect an update of the time series of the measured volume transport next year.
Okay.
Yeah, it's work in progress, and it's very exciting results. Thank you very. Can I ask a question, maybe?
Yes, please, Laura.
Thanks a lot, Dmitry, for a shocking talk. We have to change all the mooring array.
No, not at all.
Put everything on the shelf.
Not at all.
Yeah, okay. So anyway, but I have two questions maybe. I think in all three model runs, you showed that there is, in the mean, a northward flow still along the coast. Is
Yes.
that true? So also, so that's an annual mean or a long-term mean, or that's year-round?
In terms, this is the long-term mean, and I assume that Rasm and Nemo also showed the long-term means.
Correct.
Yeah.
Okay, yeah. So there is some, but that's interesting. So that's also happening in the winter then. Still, that's kind of interesting feature.
The northward flow, yes, it is interesting. It is interesting.
Yeah. Another question then. Okay, you showed that our shelf mooring F17, that's at 8 degrees west. You cannot find any relationship with the time series of that one. It could not be serving as a proxy for the flow on the shelf. But then you can tell me where I should put a mooring which does capture the flow on the shelf as a proxy, for example. So could you find out which longitude would be the best place to measure in order to get an idea for the flux on the shelf?
And I don't know the answer right now, but this is definitely a good question. There could be some problems with the approach that I tried. This simple linear regression may be not the best model to find the relationship between observations at this location and the overall freshwater flux on the shelf. And we could try something else.
Dmitry, if you go back to your nice velocity Hovmöller diagram, Dmitry, isn't it, I mean, on 12 west, you have the core on the shelf, don't you? There, right? So on the 12 degrees longitude, that's where you have a core flowing south.
Yeah, you're right, Lars. Another idea maybe to use some information from the sea ice flow. And maybe the sea ice flow can somehow help us to reconstruct this missing part on the Greenland shelf. Because I think that salinity is not more or less known on the shelf. What is missing is the velocity, right? And if we could somehow reconstruct velocity on the shelf from sea ice, we can reconstruct the freshwater flux.
Thanks. Yeah, well, it's at least to help a little bit, we did deploy a mooring last September at about 10.5 degrees west. So we are trying to measure there right now. Yeah. Still a tricky area though with icebergs.
Oh yeah, so. Yeah, I'm sure. Yes.
But thanks a lot for a cool talk.
Thank you. All right, I think it's time to wrap up. And I don't know, Wilbert, Shujin, do you have anything to mention, to add?
I don't know if you can hear me, but I don't have anything to add. It was a really, really interesting session today. Thank you, Dmitry and Wieslaw, for these very informative presentations. And they were a very nice complement to the session that we had a month ago with the Norwegian. So thanks very much. Susan?
Yeah, I echo Wilbert's comment. A very good talk. Thank you, Dmitry, and also the participation of all everybody. Very good questions, and I really sense you really want to know from modelers, like from observation side, where we should put observation to help a model, and vice versa. So the integration really important to identify the knowledge gap and how design the observing network, etc. So very good discussion. Thank you all. Yeah.
All right, then thank you everyone. And we don't have yet any plans for the upcoming meetings, so please stay tuned. With that, thank you everyone for attending this meeting, and have a wonderful holiday season, and see you all next year. Goodbye.
Great. Thanks everybody.
Thank you.
Thanks, Anne.
Bye.
Thanks.